Start recording here. But so yeah, we are going to skip chapter 18 and go into chapter 19. This set, yeah. All right, we are recording. I am going to share this screen with you. There we go. All right, now we're in business. Woohoo! So yeah, chapter 19. Well, you can see by the title here, wonderful, wonderful new stuff, and I know everyone is extremely excited. But well, all right, so we get a new term today, and I mean it's a little different, but it goes in lines with everything else that we're examining. Notice the term reactance, right? Now we've dealt with capacitive reactance up till now, but now we deal with inductive reactance. So let's take a look at the highlights. This chapter is actually a little on the short side. It's more of an introductory into inductors. Um, and so as you can see by the topics that we cover here, we're going to look at something called X of L, which would be the inductive reactance. So the L is our a new letter, I suppose you could say, where L stands for inductor, C for capacitor, R for resistor, and those three elements will make up an overall where I know recently we've gone into what Z is, right? What the impedance. Well, all three of these will be under our umbrella as like AC um, impedance altogether, right? Reactances and resistances. So inductors react, capacitors react, but inductors don't react the same way as capacitors. And the thing about inductors, another basically a reason why we didn't cover them in DC is they literally do nothing in DC. They're essentially a coil. So the way like a DC current views an inductor is pretty much a short. So we've seen like with the capacitors, right? How does DC react with that? It's basically a cap gets full to the charge and then becomes an open circuit. Well, this is the other side of the coin, or inductors. They don't necessarily charge up per se, but because of just a coil, there is no reactance in DC current. So literally all it is an extremely long strand of wire. And later on, we'll get into in a separate class, but actually looking at like resistivity of copper wire. And I mean, there is going to be a certain amount of resistivity, even in a conductor, but I mean, overall, it's very low, which is one of the reasons why we like to use it. But when you make an extremely long coil of it, as far as like DC applications go, it's just an extremely long wire. Whereas AC is different. But we'll get into that. But basically, so what are some of the topics we're going to look at here? We have our new term X of L, which would be inductive reactance. And notice that this one reduces the amount of I current, right? So before we had a reactance more against voltages. Well, now we have inductors which are reacting more against current. And we'll gloss over here with our new term of what X of L is equal to, because that, remember, now we have an inductor, okay, and it'll have a certain rating to it, and it's measured in what they call henries, and that's due to basically because of the coil. So our inductors you'll see an H and whatever number that they have with it, millihenries and so on. There's quite a range actually of inductors, sizes and shapes and whatnot. But essentially, at the heart of all of them, it's literally some type of coil, a strand of conductive material, really, that we're going to induce like an electromagnetic effect with, right? Anyway, but so our new thing is the X of L. So inductive reactance, and what is it equal to? 2 pi FL. So notice this is a direct relationship. Yeah, I know I'm babbling on, but it's 2 pi FL, and we're going to go into that. We'll be looking at series or parallel inductive reactance, how Ohm's law applies with X of L, applications with frequencies in X of L, what kind of reactances we can expect, and even a type of wave shaping, from AC sources, what kind of wave shaping we'll be looking at. So whether we're having like that lead lag effect and whatnot, we're going to be, well, we'll get into that here. Let me go to the next slide. So our first broad statement, an inductance can have an appreciable X of L in AC circuits, which will reduce the amount of current. So, like I said before, we had with capacitors where it was affecting the voltage, right? So we get into a term, you'll probably hear this from time to time, but they say it's Eli the Iceman, which is a mnemonic for, for memorizing. And the way it goes is it's, okay, Eli, I mean, I don't mean Eli in the class, but it's ELI, right? Now think of the terms in Ohm's law. So the L in the middle stands for inductor, and then we have the E coming to the front and the I at the end. So in this case, voltage is going to lead the current, whereas in X of C, this is where the ice comes in. So now the C in the middle of ice would be for capacitor, and then you have the I and the E from our terms, right? Where now we see the phase differential going on here. So it's a mnemonic to remember. We'll go in. I'll be using it from time to time. So, but yeah, Eli the Iceman, kind of a your little new mnemonic of the day, I guess. Um, but anyway, getting back to the subject matter here. So the higher the frequency, the greater the L, because now we're not in an inverse relationship. Whereas before, like the capacitive reaction formula, was an inverse relationship, 1 over 2 pi FC. Whereas this formula is there's no 1 over X of L is equal to 2 pi FL. So it's a direct relationship. So if I change the frequency up or down, it will directly cause X of L to go up or down. And the same with the value of the inductor, right? And again, 2 and pi are fixed. And like I was saying, I say the very bottom statement, there is no X of L for steady direct current. And there isn't. It's like he states, it's a coil. And the resistivity of wire is pretty minimal. But so here we go and look at how X of L reduces the amount of current. So he draws us out a nice little circuit. The very first one is just a simple, right, series circuit where we got an AC source feeding into a light bulb. Now the second one, we look at B here. So notice there's our new symbol. See how it's like looks like little lumped up hilltops. So seeing one of those, something like that, that is the symbol for inductors. It's supposed to be like a coiled wire type thing. And then what he has drawn up above top there, you'll see those 2 parallel bars. That's, see, a lot of times with inductors, what they'll have is air transmission from like one coil to another. And so what that signifies is the permittivity there. So if we were to have another coil on the opposite side of that, the one coil would induce or affect the other coil. But anyway, so he goes into and he's showing how. So notice in the very top one, just the energy source in the light bulb, that the current is equal to 2.4 amps. Okay. Now, if we look down in the middle one, you notice there we have an R potential of 1 ohm here with the R of the light bulb at 50 ohms, but now we have a current of 0.12 amps. It's an interesting thing. So how does he, let's take a look at his statements here. So if we look at figure 19A, 19.1A, There is no inductance. The light bulb is glowing at the full brilliance that it's allowed to glow. But in the middle one, the coil is connected in series with the light bulb. And as he states here, the coil has pretty much no DC resistance, right? 1 ohm, which is pretty minimal. But notice it has a reactance of 1,000 ohms. So as far as our reactance against AC, it's kind of high, right? 1K. So if we do the Ohm's law situation, we have where if the we have 120 volts divided by 1,000 ohms, we get 0.12 amps. Yeah, and that won't be quite enough to light up the light bulb. But notice in the very bottom one, he changes the AC source to a DC source, and that changes everything. Right now, we have enough brilliance to light the light bulb because essentially the coil or the inductor is a short. There's really no resistivity to it. Yeah, 1 ohm of coil wire. But so reactance is an interesting thing, and yes, inductors oppose current, right? So think that in your head. Capacitors in an AC environment oppose voltage. Inductors in an AC environment oppose current. They don't really affect voltage so much, but you can see by the example here that we can affect current by quite a bit. Let's take a further look into this. And this is all introductory. I mean, we're just, getting used to some of the new ideas and new terms here. So we have our new formula here for reactance, where X of L is equal to 2 pi FL. So we can see that it is a direct relationship, and everything. So if we vary we vary the frequency, that directly affects X of L. If we vary the value of the inductor, it directly affects X of L. So in some ways, it makes it easier for our calculations because then we don't have to deal with any fractional exponents or anything like that. So he goes through and like, again, this is like an introductory thing, but yeah, the frequency is a time element. The inductance L indicates the physical factors of the coil, because coils, they're all about internally what they call windings. And what that means is how many times around or, in a loop do we have. So because the more coils that you have, the more of an electromagnetic effect that you're going to induce. So the greater the amount of wraps or the greater the amount of turns you have in a coil, the greater the overall reactance will be of that particular coil or inductor, if you will. So let's take a look. He jumps right into it. So now we're like old hands at this, right? But we had a trial by fire with capacitive reactances. So this should come a little easier to absorb, but we'll go through it. I'll have, when we'll have the labs and practice problems for this. And of course the homeworks. Everybody loves the homeworks, but anyway, so since reactance is an opposition in ohms, right? It does oppose. It is gonna block or do something with an energy source and not just simply let it through. Um, we have to look at how it's reacting. So with series reactances, so we'll be taking a look at these and seeing how we sum up the inductors in a series environment and how we sum them up in a parallel environment. And I remember there's going to be two types of things here where one, if we deal with X of L and these environments, that's one type of thing where we're actually looking at reactance. Now, if we're looking at just straight values of L, that becomes a separate thing. But so don't confuse the two. but it just works the same way. So if we let's see, if we looked at it and we wanted to find out, okay, what's the overall reactance in this case? So he states that the X of L1 here is 100 ohm, X of L2 is 200 ohms. And it's pretty straightforward, right? Just as any series environment, we just add the 100 plus the 200 and come up with 300 ohms. And then down in the next one over here in a parallel environment, we have 100 and a 200. And what are we going to do? We're going to come up with a parallel equivalency, right? And doing the inverse function, and you can see it comes out lower than the lowest one in the mix, and we come up with an equivalent of 66 and 2/3. So kind of like opposite of what the capacitors worked like, right? A little different. Anyway, so take a look at a couple of circuits with this. Now, these are purely inductive circuits. And notice there's no resistor element in there. We don't have any capacitors mixed in with it or anything. This is just straightforward inductors. Um, and we could see by a couple, I mean, we're just doing straightforward Ohm's law, right? With the very first one, if we look where the current is equal to the voltage divided by the amount of reactance. And he uses straightforward numbers, right? 100 volts, 100 ohms. And so just doing Ohm's law, we come up with an overall of 1 amp for this circuit. Now in the next one, we have two components in series and they're equal. And again, notice because now we have double the amount of reactance in this case. We got half of the current that we did in the previous circuit. And looking at a parallel environment, remember, what is different or unique about parallel is the current changing, right, from branch to branch. So we do have which should be separate currents, but in this case he uses equal components, so they have an equal split. So we get 1 amp in each leg and add those two up together, and we come up with an overall source current of 2 amps. So pretty straightforward overall. I mean, like I say, the only really new thing that we're going to be dealing with is the concept of the inductor, but and the new formula of X of L is equal to 2 pi FL. But everything else, we're just building on what we've learned previously with AC. So he just has some very generic examples of what kind of frequencies we can expect. And again, like in power lines and things like that, yeah, you're going to expect a pretty low frequency. The medium audio frequency, like the AM bands or the ham radio and stuff like that, they'll be like a mid range. And then we start getting up a little higher. Now we're actually in AM where they call high audio frequency. And then past that, it's the FM broadcast range. um, but basically, he's making a point by, doing a 2 pi FL. So we just plug through and use the formula, and you can see that as the higher the frequency goes up, the smaller the reactance. It's a direct relationship. There's no fraction that we have to deal with, so no inverse. So notice that at the low frequencies, the henries are very high, and at the higher frequencies, the henries are very low because that's micro henries. We went from henries to micro henries, and essentially using the very same inductor, right? It's the same inductor value for each one of these. So the only thing that did change was the frequency application. And you can see how it affected the value of the reactance by quite a lot. And so it could change an inductor, the X of L value drastically. An interesting thing, which we will be using later, though. But but yeah, this is, I mean, my bad. This is a kind of a short chapter. Like I say, he just does introductory. So you guys will be happy. It'll be nice for the weekend. But anyway, so we go into talking about the wave shaping and what we're going to be recognizing. So when we view it on the oscilloscope. So his first broad statement, induced voltage depends on the rate of change of current rather than on the absolute value of I. So what the heck does that mean? Well, really, it's the frequency, right? The rate of change. So how fast the current is going has a much more effect than the absolute value. Like if I were to say like this is 10 amps or 5 amps or something like that, the frequency has a much more adverse effect upon the value of the reactance actually. But anyway, so if we were to look at an inductive voltage curve that is 90 degrees out of phase. It's a cosine wave again, which should be a familiar term for us. So again, this one has, so now instead of, now remember, X of C had a negative 90 degrees out of phase, right? So this one has a positive 90 degrees. So it's going the other way. So X of C affects it by 90 degrees. So we were to have a phasor, right? We had that phasor and it goes into the negative region. Now this would be the opposite side of that. And if we were to draw a phasor, it would be a positive one where we would be going up, and because it's a positive 90 degrees out of phase. So just something to note. Um, and again, if frequency is equal to 1 over time, and flip side of the coin, time is equal to 1 over frequency. Which I think you guys have been doing pretty good with. I mean, looking at the scopes, I know these scopes help a lot because it gives you the values, but um, and then the very bottom statement is Ohm's law statement, right? Specifies the inductive reactance, and again, it's in ohms. So any type of resistance, reactance will be measured in ohms. So now we take a look at a curve, a couple of curves. We should be more familiar with recognizing what the heck is going on here. So if we were to look at, okay, the red one, all right, versus the blue one, we could see what's going on here. Now I know we throw a derivative statement in here, but the way to read those, I don't know if I mentioned it, really all you have to do, the D is, it stands for derivative. You derive, and basically what it is, it's versus time. So you would find out like, what is my value at this particular moment in time, okay? But what are we measuring? So really we look at the second term, which is the I. So what we're measuring is the current, or the changes of current versus the changes of time. So as it changes, we do, because we do have these alternations going on over a certain amount of time, and that's what the statement says. So he's saying that V sub L is equal to the amount of inductance times the amount of current at a specific moment in time, because I mean it's constantly changing. So if I were to say, like here, my magnitude there is going to be different than if I were to pick here or here. So, and that would be right with respect to time, how much current I have. Anyway, but we can see we've got another 90-degree shift, but now it's in the opposite direction, if that makes any sense. Anyway, but like I say, this is all introductory. We'll be going into this more in detail, and we will have the lab so we can observe the effects of how the inductors are reacting. So here we have a voltage and current curve. Okay, you can see our little phasor type diagram, a red one versus the blue one, right? So this is a voltage versus current. So the blue one is the current and the red one is the voltage. So if we were to look, we could see that the voltage is coming in, and then we could see that the current is definitely out of phase with the voltage at this point. And that's the inductive effect. It will do that. But again, like I say, it's a different direction than the capacitors. In fact, it's completely the opposite direction, if you will. So here we go, our two statements of what this is. We have the application of the 90-degree phase angle in a circuit. So again, we're back to phasor diagrams. We would still have to do that and apply Pythagorean's theorem generally when computing these, especially when we get into mixed elements with these particular things. So of course, we're going to do inductors first, and then we'll go in and add in the next chapters. We'll add in the resistors with the inductors, and we'll be playing around with different mixtures of components with these and seeing how they affect each other and what our end results are. Anyway, but yeah, the phase angle of 90 degrees between V and I will always apply for any inductor with the sine wave because it's reacting, and how it reacts is that particular way. So again, so capacitors, opposing voltage, inductors, opposing current. And we can expect that every time. So here we go with a mixed circuit, and we have quite a bit going on here. We have a series parallel mix of resistors and inductors. And so let's take a look at what goes on here. So if we say here, right here where I1 is, right? So current I1 is lagging, and here we got BL1, right? So we're establishing a voltage across this particular inductor here, and by 90 degrees. Now we go to the next leg and we see I2, right? Current lags right here, BL2 by 90 degrees. And then finally, we look at what I3, which would be kind of like our I total, if you will. But again, current is lagging BL3 by 90 degrees. So, and it's a specific reaction of these inductors. That's what they do. They oppose the current, and every single time we'll be out of phase by that 90 degrees. So always keep that in mind of what's occurring when we look at these circuits. And that's the end of the slides with these. It's like I say, it's a short chapter, but it's introductory. So we'll do the homework from this and we'll study these a little bit. I won't be giving out practice problems for these next week, but we'll probably be getting into chapter 20 by that point, and then I'll have practice problems to back it up so we can work them through, and of course the labs. But remember, next Tuesday, no lab because of election day. And then today I'll post the homeworks for chapter 19, but it's short. It's short. And remember too, on the homeworks, you should be able to, I'm pretty sure I set them up where you should be able to go in and submit them late if you need to for whatever reason. And I still go through and grade them. I might knock you off a couple of points for being late, but it's better than no points. But yeah, if you have to go through or if you need to do anything late, let me know. And I'm pretty easy to work with. Like I said, I just want to keep us focused and going with the pace of the class with all of these concepts, because it is quite a few things, and we're trying to go as quickly as possible. So this is what we have ahead of us for like the next week and a half, because we'll be going through 19, 20, and 21. We'll be examining inductors, and of course, we'll be looking at series parallel combinations and then throwing resistors in the mix. And then eventually what we'll do is, no, let me get out of that. We'll stop staring at that. Anyway, you stare at my ugly face instead. Where the heck was I saying? But no, we'll be looking at combinations. And of course, if you think about it, where we're headed with this, we're going to be doing a mix of all three, where we have RLC circuits, and that'll be like our as we get to the end, and we'll be looking at actual practical applications of what we would do with these things. So we'll be doing looking at what they call filters and whatnot, and these have a wide range of applications. And granted, I will say that's largely with like communications ends, because you want to keep your communications as crystal clear as possible. Excuse me. So we'll be using these type of things to smooth out our signals, but we'll show you how that all works. I'm quite excited. I know you will be, but that's what we have coming up ahead of us. And now we're going to be looking at inductive reactances, kiddies, for the next, like I say, the next week and a half, and then we'll be playing with combinationals of these components and seeing how they react. So I'll be handing out, like tomorrow, I'll hand out some more practice problems for you for the weekend. Basically closing out the capacitor end of it. We'll be it'll be RC parallel equivalencies, because we've done RC series. So I'll hand out practice problems for RC parallel tomorrow. Might have I'm not 100% decided on what lab we're doing tomorrow, but we will have a lab tomorrow. I promise. So we'll do that. I'll hand out the practice problems, and we'll go over. And again, if anybody's struggling with anything or anything like that, definitely let me know, and we'll work it out. we'll either work, do some work. It's harder for me to do demonstrations and stuff on here. I'm not gonna lie. It is a lot easier in the lab environment for me to do demonstrations for you. So if we do need to work some things out, we'll do like we did yesterday, and we'll go over, a problem or two together and make sure we're all following the same steps. But as far as that, the rule sheet that I gave you, right? That all the formulas on them, right? Those apply basically for every type of thing. If you see through there, we have like series parallel combinations of both capacitive reactance and inductive reactance. So eventually we'll be using everything on that sheet, but I think we're all headed in a good direction. So we'll just keep focusing. And like I say, I'll probably either have that homework for 19 either post it today or yeah, probably today. Yeah, we'll do that today. It's a short one. It's not like the rest of them where you have like an insane amount of questions. So it'll be short. And then I haven't decided if we're going to have a quiz combinational. I probably won't. So we'll probably have a quiz on chapter 17 over the weekend. In fact, I'll probably do it for both days. So that way we close out the capacitive reactance, and then we'll have everything focused on the inductive reactance for the next week and a half. So expect to see that. We'll have a homework. We'll post that sometime today, and then, like I say, probably by Friday, I'll have a quiz posted up, and then yeah, we'll have a new lab tomorrow where we'll try to finish up our capacitive reactances, and then we'll start jumping into inductive reactances. All right. And that's pretty much all I got for today. And then we'll see you guys all bright and early tomorrow. Any questions on any of that, or we're all good? Does that make sense? All
All good.
right. But yeah, if you have any questions, hit me, or you know how to get a hold of me. Email me. You can text me if you want. I really don't mind texting. Trust me. Just make sure you tell me who you are, because it's just gonna come up with a phone number. I get enough weirdos now. But yeah, if you need to, go ahead and text me, and then or feel more comfortable, email me. Either way works. I'm a little slower on the email response, I will tell you. Texting me gets you a faster response. Just an FYI. But yeah, other than that, I'll see you guys. We'll see you guys tomorrow. We'll jump into some new stuff, and we'll get her going. All right.
Have a good one, Tom.
Oh, you too.
Have a good day.
You too, sir.
See you tomorrow in lab.
See you tomorrow.
All right. All right.